This Soviet machine carried 6 anti-ship missiles, each one capable of crippling an American aircraft carrier. It moved at 500 kilometers per hour, fast enough that a destroyer would have under a minute to react, and even American radar, the best in the world, could not see it coming. It worked and did everything it was designed to do. But why did the Soviets only build exactly one and walked away from it entirely, leaving it rusting on a beach? In 1968, an American analyst stared at a satellite photograph of the Caspian Sea and could not tell whether he was looking at a ship or a plane. The object was 100 meters long, heavier than a fully loaded airliner, and it was moving at aircraft speed while sitting on the water. He filed it under 2 letters, KM, and the CIA quietly renamed it the Caspian Sea Monster. But the Soviets already had a word for it, and for the entire class of machine it belonged to, Ekranoplan. What broke every category was simple. It stayed pinned to the surface on purpose, and for 14 years nobody in the West understood why that was the entire point. Start with the number that made analysts distrust their own eyes. The Ekranoplan weighed roughly 500 tons fully loaded, comparable to a modern wide-body airliner sitting on a runway, except this thing was doing it over open water. An object that heavy should not fly at all with the wings it had. Its wingspan was short and stubby, nothing like the long, graceful span an aircraft that heavy would normally need to fly. By every rule taught in an aerodynamics classroom, those wings were too small to lift that mass. And yet the photographs kept showing it moving, fast, level, and low. Here is the assumption almost everyone forms first, and it is wrong. You look at a plane that can only fly some meters above the water and think, it can't get off the ground, it's a failure, a heavy machine that never worked. That reading is completely backwards. The Ekranoplan could climb. Its engines had power to spare. Staying low was a choice its designers fought to preserve because leaving the surface would have thrown away 3 separate advantages at once. To understand why, you have to understand what happens to a wing in the last few meters above a flat surface. When a wing moves through air, it generates lift, and it pays a tax for that lift, a form of drag created by the swirling vortices that spin off the wingtips. Those vortices are pure waste. They are the reason long-haul aircraft have those upturned tips at the end of the wing, small devices whose only job is to fight that swirl. Now, bring the wing down close to the ground. Within roughly 1 wingspan of the surface, the ground physically blocks those vortices from forming. The swirl has nowhere to go. The waste drag collapses. This is ground effect, and pilots feel a mild version of it in the final second before every landing when the aircraft seems to want to float. The Soviet engineer Rostislav Alexeyev did not treat ground effect as a nuisance to be flown through. He treated it as a place to live. Alexeyev had spent his career designing hydrofoils, boats that rise on underwater wings to escape the drag of water. He understood better than almost anyone that drag is the enemy that decides everything: your speed, your range, your fuel bill. And he had run the numbers on what happens if you keep a wing permanently inside ground effect. The collapse in drag is not small. A wing designed to stay in that band can be dramatically more efficient than the same wing flying free, which means the Ekranoplan's stubby wings, useless at altitude, became enough down here. That is why it stayed low. Rise out of the effect and the physics that carried 500 tons simply switches off. Now, the second advantage falls out of that same low altitude, the one that kept American analysts confused for 14 years. Radar works by line of sight, and the horizon curves away. A target flying at 5 meters over the sea drops below an enemy's radar horizon at a fraction of the distance a high-flying aircraft would be spotted. Sea clutter, the messy returns bouncing off the waves themselves, swallowed what little signal there was, so the Ekranoplan did not need stealth shaping or exotic materials. It hid inside the geometry of the planet. The same 5 meters that made it terrifyingly hard to fly made it nearly impossible to see coming. And there was a third payoff, the one that made the Soviet military take it seriously as a weapon. Collapsed drag means collapsed fuel burn for a given speed and load. An Ekranoplan this heavy, moving this fast, was more fuel efficient than a conventional transport aircraft carrying the same cargo, because it was not paying that wingtip vortex tax the whole way. So it was faster than the ships it could outrun, lower than the radar that hunted ships, and cheaper to run than the planes that could match its speed. On paper, it was a machine with no natural predator. That is why leaving the surface was never on the table. Every single advantage, the lift, the invisibility, the fuel economy, was a rent paid only inside those bottom few meters, and climbing canceled all 3 at once. That sounds like exactly the weapon you'd want, and for a while, it was. But building it exposed a problem nobody had solved before, because no one had ever tried to fly this heavy, this low, this fast. That single choice created a problem that nearly ended the whole program before it started. If your machine only works within a few meters of a surface, the surface had better be perfectly flat, and the open sea is not flat, so waves became its biggest enemy. Early Ekranoplan concepts failed here in a way that was easy to describe and hard to fix. A gust or a swell would push the craft up out of the effect, drag would slam back on, the nose would drop, and the machine would be shoved back toward water it was traveling across at hundreds of kilometers an hour. The margin for error was measured in single-digit meters. Get it wrong and you don't stall gently at altitude, you hit the sea. Consider what that meant in practice. In a sea state with waves of 3 meters, an ordinary day in most of the world's oceans, a craft cruising 5 meters up has almost no margin, and a single large swell isn't just turbulence. At 500 kilometers per hour, striking water is closer to striking concrete. The machine that could beat radar and beat interceptors could be defeated by weather that wouldn't trouble a fishing boat. And he failed approaches piled up. Simple flat wings held too little of their lift when they dipped and pitched the craft nose down toward the water, unrecoverable at speed. Pure hovercraft designs which rode on a cushion of trapped air solved the wave problem but capped out at low speeds and could never approach what Alexeyev wanted. Small experimental Ekranoplans built by other designers worked over glassy lakes and became lethal the moment real swells arrived. Each failure taught the same lesson written in a different accident. Staying in the ground effect band was easy in theory and murderous in practice. Alexeyev's fix is the reason his Ekranoplan looks so strange. He put a huge horizontal tail high up on a tall fin, deliberately lifted out of the ground effect the wings lived in. Because that tail flew in normal, free air while the wings did not, the two surfaces reacted differently to any disturbance. When the craft rose too high, the tail's behavior automatically pushed the nose back down toward the surface. When it sank too low, the balance reversed and eased it back up. The machine was tuned to trap itself inside the correct altitude band, without the pilot fighting for it every second. He also mounted engines at the very front, angled to blow air under the wings during takeoff, forcing a cushion beneath the craft to break it free of the water's grip before speed took over. Consider what one of those test flights actually asked of a human being. The lead test pilot flew this 500-ton Ekranoplan at around 500 kilometers an hour, roughly the cruising speed of a passenger jet, while holding an altitude of about 5 meters above open water, hour after hour, with no room to recover from a mistake. There was no ejecting up and away from trouble. Up was where the danger lived. The entire flight envelope was a corridor a few meters tall, and the job was to stay inside it over a sea that would not cooperate. The Soviets pressed on anyway because the tactical promise was too large to abandon. The first machine, the one Alexeyev built as a test bed, was 100 meters long, longer than a Boeing 747. Western intelligence, staring at satellite images of a thing that size moving faster than any ship, gave it the only label that fit their confusion: the Caspian Sea Monster. It flew for years on the Caspian Sea, a body of water chosen precisely because it was enclosed and relatively calm, and that choice tells you everything. The Ekranoplan could only be tested where the ocean's worst behavior was kept out. Then, in 1980, the Sea Monster crashed. Pilot error during a maneuver, a wing caught the water, and the largest flying machine on Earth sank. No one was killed, but the prototype that had absorbed years of work was gone in seconds, a blunt reminder of how little room the design left for a single mistake. Out of that program came the Ekranoplan on the beach today, the Loon. This was the weapon, not the test bed. Around 380 tons over 70 meters long, and mounted on its back were 6 massive launch tubes carrying anti-ship missiles designed to cripple a carrier in a single pass. Flying below radar at 500 kilometers per hour, it could close on a carrier group and launch before the defenders understood a threat existed. The concept finally was fully realized, and it worked. And then the world it was built to fight simply went away. The Loon entered service in 1987. 4 years later, the Soviet Union collapsed. The enemy carrier groups it was designed to ambush were no longer the organizing threat of the state, and the money to build a fleet of these Ekranoplans evaporated overnight. But the collapse only finished a job the physics had already started. Even in a world with unlimited rubles, the Loon's problem never went away. It was a weapon that could only fight in good weather, confined to sheltered seas, one bad swell away from destruction, and requiring 8 thirsty engines and a specialist pilot to do what a submarine could do in any conditions, hidden at any time of year. So they built exactly one Lund-class Ekranoplan, canceled a second that was half-finished, and let the program die. The machine that American analysts couldn't classify, the weapon that worked exactly as designed, was undone not by an enemy but by the sea it was born to skim across. Today, the Loon sits beached on the shore of the Caspian, hull streaked with rust, launch tubes empty, still 380 tons of realized impossibility. It never lost a battle because it was never sent to one. And the idea hasn't fully died until this day. Designers still sketch Ekranoplans for cargo, rescue, and even passenger transport, chasing that same cushion of trapped air, still fighting the same unforgiving band of altitude that no one has yet learned to widen. The Americans also built their own machine around trapped air, but in the opposite direction. Fold the wings down at 3 times the speed of sound, and the shock waves coming off the airframe have nowhere to escape either. The same principle pressed into service 70,000 feet up instead of 5 meters above the water. It had 6 jet engines, and it was so fast its own paint peeled off in flight. Then something happened during testing that ended the program, and only one of the 2 aircraft ever built still exists. To know why this incredible bomber that could outrun every interceptor the Soviets had was scrapped, click this video.